This is the first of 3 lectures which comprise topic 2. If you take a look at the the course outline, topic 2 talks about PN junctions. Okay, we're going to do an electrostatic analysis of the PN junction. We're going to see how that results in a diode and also how 2 PN junctions can be used to form a bipolar junction transistor. So this first lecture is going to touch on basic electrostatics and the PN junction. By the way, topic 2 will consist of 3 lectures or 4.5 hours. So this is what we're going to cover in this particular lecture. First, we're going to take a look at diffusion and drift in a non-uniformly doped semiconductor. Then we're going to go into basic electrostatics and band bending. And finally, we'll take a look at the electrostatics of the PN junction. Okay, let's consider the case where you have a non-uniformly doped semiconductor. Okay, so this is a hypothetical case, a hypothetical N-type semiconductor whose doping level varies linearly along the x-axis. So imagine this semiconductor bar. This is very heavily doped with donor impurities, and as you go along the x-axis, the level of doping gets lighter and lighter, so that at x equal to L, it is already very lightly doped. We can consider the doping, or we can let's assume that the doping profile is linear. No? So here you have high doping and then linearly decreasing. Here you have low doping. Okay, what's going to happen? The instance this semiconductor is created, let's assume it was instantly created with that kind of doping level, because of the non-uniform concentration of electrons, the natural thing to happen will be diffusion. You have more electrons here, no? Less electrons here, and therefore you expect electrons to diffuse along the x direction. So initially there's going to be diffusion. As the electrons diffuse, the area where the electrons left become positively charged. And as more electrons move toward the right, the area where the electrons end up being become negatively charged. So you have a charge distribution, or you end up having a charge distribution in your semiconductor. Again, no? Bakit positive to, no? Ba't nagiging positive to? Kasi yung atoms natin inaalisan ng electrons, no? And therefore it becomes net positively charged. No? At kung saan man pumunta yung electrons na yon, that area becomes negatively charged. No? So diffusion causes the left end of the semiconductor to become positively charged with respect to the right end. When you have a charge distribution, expect an electric field to build up. So as the electrons diffuse, this electric field will start building up. And the electric field will be in the direction of the x-axis, because we know that an electric field originates at positive charges and terminates at negative charges. But what happens when there is electric field? No? What happens when there are charges in the presence of an electric field? No? We studied that last lecture, last module. No? Whenever there are charges in the presence of an electric field, those charges will experience a force. And that force will make those charges move. No? So for electrons, what direction will the electrons move? They will move opposite the direction of the electric field. No? No? So there will be electrons diffusing from right to left, no? And then there will be electrons drifting, because it's in the presence of an electric field. There will be electrons drifting now from electrons diffusing from left to right, and there will be electrons drifting from right to left. Okay. At some point, no, there will be an equilibrium condition where the diffusion and the drift cancel each other out, resulting in zero net current, which makes sense because how can you have a current flowing in an open circuited semiconductor material? No, there's no closed circuit here, so how can you have a current flowing? No? So eventually, the diffusion and the drift will cancel each other out. Okay, and you will have zero net current. So that is the steady state condition. But then your electric field will stay there, no? Because you have net positive charges here and net negative charges there, no? If the electric field disappears, what will happen? There will be diffusion again, no? So the electric field will have to stay there. Now, what does that imply? Whenever you have an electric field, that means there is a potential difference, no, between the left side and the right side. Or there's going to be a voltage profile along the x-axis. There's going to be a change in the voltage or the potential along the x-axis. So we want to explore that voltage some more. Okay. We want to explore that voltage some more. Okay, so let's go back to the non-uniformly doped n-type semiconductor. So there will eventually be a charge distribution. Okay. Let's assume that that charge distribution will be linear. No? It may not be linear, no, but let's assume it's approximately linear. Okay, where the left side is net positively charged and the right side is net negatively charged. And it must be true that plus Q will be equal, that the magnitude of the positive charge will be equal to the magnitude of the negative charge, because your semiconductor to start with is neutral. Okay, this is an equation that you will learn, or you might have already learned in EEE 135 in your electromagnetics course. This is Poisson's equation in one dimension. What does Poisson's equation in one dimension say? The derivative of your electric field intensity with respect to the dimension of interest, or in this particular case, no, with respect to x, one dimensional, is equal to the charge concentration or the charge density divided by your permittivity, divided by the permittivity of the material. So that is this equation. The derivative of your electric field intensity with respect to x, assuming that your electric field intensity varies along the x, is equal to your charge density divided by the permittivity of the material. You must have taken up permittivity already, either in 135 or in physics, that sort of measures the property of the material to retain or to support an electric field. If we solve for electric field intensity in this equation, you get this particular integral. Where, what is this? Let me annotate. Where, what is this? This is the area under the charge density curve. That is the area under the charge density curve. No? So what are we saying here? If we know the charge density profile along the x-axis of a semiconductor, we can actually determine the electric field intensity along the same axis, because this is just proportional to the area under the charge density curve. You just divide that area by the permittivity. So let me give an example. This is hypothetical, but let's assume your charge density looks like this. Your charge density looks like this. Charge density is charge per unit volume from the length 0 to L. What will the plot of the electric field intensity look like? So remember, electric field intensity is of x is equal to 1 over epsilons of s, the integral of rho dx. So this is the area. What will your area look like? What will the area of this curve look like as you are going from 0 to, let's say this is L over 2. What will the area of that look like? As you're going toward the right, the area will be increasing. Again, as you're going toward the right, the area will be increasing, and the rate at which it will be increasing will also be increasing. It's going to be a negative area. So starting here, our area is 0. Maybe here, your area will increase. Here, your area will increase more. Here, your area will increase more. Here, your area will increase more until your area is this, So you might get a curve that looks this way, It's a curve. Whereas you're going to the right, your area will increase, Will increase faster and faster. Why, Because as we're going to the right, palaki ng palaki itong mga nadadagdag na mga area segments. Okay? So what will this be? What will this point be? Okay. This is A1, where what is A1? A1 is the area of this particular triangle, That's this. That's A1, no? Sorry, over ES, A1 over epsilon of S. Okay, now what happens here? You have a negative area. All of a sudden, idadagdag mo tong area to, So your negative area will now become less negative, okay? So first, it is becoming less negative quickly, but it will become less negative slower and slower, Okay, so you're going to get a curve this way. Okay? Where eventually your total area is 0. Why? This is A2, and A1 is equal to A2, So your final area is 0. Your final area is 0. So if I know, again, if I know the charge density profile, I should be able to visualize what the electric field intensity will look like. So in this particular case, this is what your electric field intensity will look like. Okay, continuing with basic electrostatics. Again, this is by definition. Electric field intensity is the negative gradient of voltage. Electric field intensity is the negative gradient of voltage. So E of x is equal to negative dVx dx. Again, if we solve for V of x here, we just get the negative area under the electric field intensity curve. So this is the area, again, area under the E of x curve. So what is the significance of this? If we know what E of x looks like, if we know what the profile of E of x looks like along the x-axis, we will have an idea of what the profile of the voltage will look like. This is just the negative of the area under the electric field intensity curve. So going back to the previous example, or this example, sorry, this is a nicer drawing now. Okay, so this is now the electric field profile. So what will the voltage profile look like? So Okay, we're now getting the negative of this area. We're now getting the negative of this area. Okay, so uh, that will start out negative, no? The negative of negative is positive. That will start out small. Okay, it will slowly increase. Okay, something like that. No? But at this point, the rate of increase will become slower, no? Until it will no longer increase. No? So what is this eventually going to be? What is the voltage eventually going to be? The voltage is actually going to be equal to this area, no? This area. Okay, so that's what the voltage plot along the x-axis will look like. Something like that. So sorry, no, di ko masyadong na trace yung actual plot, no? But it will look something like that. Now, voltage at any point in a semiconductor can be used to determine the potential energy of a charge at that point. You have again from electrostatics, potential energy is equal to charge times voltage. No, if you recall from EEE 123, what is voltage? Voltage is energy per coulomb, no? Joules per coulomb. No? So you multiply that by coulombs and you're going to get joules, no? This particular case, potential energy. Potential energy assumes that your charge is not in motion. Because if it's in motion, then there will also be a kinetic energy. So for electrons, because Q is negative, your potential energy is negative E, which is your electron charge times your voltage. So you will note that, excuse me, the potential energy of an electron decreases as the voltage is increasing. So if you have an increasing voltage, the potential energy of your electron will be decreasing. And in the energy band diagram, I think I already mentioned this to you before. E sub C indicates the potential energy of electrons, and E sub V indicates the potential energy of holes. Okay, so let's take again an example. So let's say this is a vacuum. We apply 1 volt across 2 parallel plates in this particular vacuum, no? Which is spaced 2 centimeters apart. 2 centimeters apart. Plot the potential energy profile for electrons along the x-axis. Plot the potential energy profile for electrons along the x-axis. And then letter B, assume an electron with 0.75 electron volts of energy is released at the left plate with an initial velocity in the x direction. How far will the electron reach? Okay, so first, what will the potential energy for electrons look like? No? Okay, if this is our reference potential, or as you are familiar with, we call it the ground. No? Okay, and then this plate, no? Remember these are parallel plates. Then this plate will be at negative 1 volt. No? So if this is at 0, if this is at 0 volts, this will be at negative 1 volt, no? Because your polarity is plus to minus. This is a vacuum. So what will the profile look like? It's just going to be linear from 0 to minus 1 volt, no? In other words, as we're going to the right, toward the right here, you might think of this like maybe like a potentiometer, no? Although not exactly that, no? Expect the potential here to be, let's say, negative 0.5 volts, no? Maybe here, 1/4 the way to be negative 0.25 volts. until it reaches a negative 1 volt potential. No? So this is how your voltage is going to look like from 0 to negative 1 volts. Okay, what will be the potential energy for an electron? So you multiply that by negative E. So this is negative, you multiply that by negative E. It will now be from 0 to 1 electron volt. Okay, so let's say I released an electron here with an initial velocity in this particular direction, and that electron has an energy of 0.75 electron volts. No? Wag na nyo itanong where it got its energy. No? There are ways of releasing electrons, for example, with a certain initial velocity. No? Dun sa mga vacuum tubes dati, they call that an electron gun. Okay? So let's say 0.75 electron volts. No? So this is the potential energy. So what is this going to be? This is going to be its kinetic energy. Okay. So that is its kinetic energy. But notice, okay, if it is going to the right, its kinetic energy will linearly drop. No? As it is going to the right, no, paliit ng paliit yung kinetic energy niya. Okay. Up to the point where no, the kinetic energy will be equal to 0, and the potential energy will now be equal to 0.75 electron volts. And that will happen here. No? That will happen at 1.5 centimeters. No? Because if this is 1 is to 0.75 as 2 is to 1.5. No? So again, no, as the electron is moving to the right, it is losing kinetic energy and therefore it will be decelerating. It will be decelerating. So when it gets to this point, its kinetic energy will be 0. Okay. It will all be potential energy, which will be 0.75 electron volts. Okay. Now, what will happen once it reaches this point? First of all, why cannot it go beyond this point? Because if it goes beyond this point, then its kinetic energy will be imaginary. No, will be negative, rather, will be negative. There's no such thing as negative kinetic energy. No? If you have a negative kinetic energy and you go back to classical physics, what is kinetic energy? 1/2 mv squared. Your v is going to end up being imaginary. Okay, if this were a real situation, the electron, as soon as it reaches here, will now start being attracted to the uh, to this particular plate. No, it will start accelerating toward the left if this were a real situation. No? Because now you will notice that it is being attracted to this particular plate because the potential here is negative, so it's being attracted to the more positive potential. And as it goes toward the left, it will continue to accelerate. It will continue to accelerate, and it will have maximum kinetic energy at 0. That's what will happen in actuality. No? Okay, what do we sometimes say? No, we say that this potential energy profile acts as an energy barrier. No, why? Because your electron cannot exist to the right of this energy barrier. No? Okay, it cannot exist to the right of that energy barrier because that would mean that it would have negative kinetic energy. Okay. I hope that that concept is clear. By the way, no, we don't expect the same thing to happen in a solid. No, so it's emphasized here that this is a vacuum. No, if I release an electron, okay, if this were, for example, a semiconductor solid, okay, this might be true. The potential energy, the voltage profile might be true. no? Because this would just look like a uniform resistor, okay? But then, if you introduce an electron on the left with initial velocity on the right, it may not reach 1.5 centimeters because of scattering. Bago pa siya dumating dito sa 1.5, it would have collided with other electrons or with the other nuclei of the silicon, and it will lose energy. So it will not be the case. This will not be the case if this were a solid. That's why it was emphasized that this is a vacuum. Okay, so again, no, let's apply, or not again, no, but let's now apply electrostatics to our non-uniformly doped semiconductor. So balikan natin itong non-uniformly doped semiconductor. No? This one, no? So we said that this is our doping profile. Okay, we're assuming that at equilibrium, this will be the charge density distribution profile. Remember that your electrons will diffuse toward the right, but it will stop diffusing. It will stop diffusing when the electric field created by the movement of electrons introduces enough drift current to counteract the diffusion current. Nonetheless, there will be a charge density profile at equilibrium, and we assume a linear charge density profile for simplicity. This is what your electric field profile along the x-axis will look like. No? Remember our formula? Okay. The electric field intensity profile will just be, no, the area under your charge density curve. No? So here, no, your area is increasing very quickly, right? No, because the segments that are added to your area are large, but as you go to the right, the segments that are added to your area become smaller and smaller. So initially it increases quickly, no, but when it reaches the middle, no, the increase now becomes equal to 0. And then what happens as we move to the right, your area now will start decreasing because this is a negative area. No, your area will start decreasing first very slowly, and then it will start decreasing more quickly and more quickly until eventually your net area is equal to 0. Why? Because the area of this positive and the area of this negative are going to be equal. So eventually your net area is going to be 0. So what will your electric field intensity look like? It will be 0 at both ends of your semiconductor, and it will be maximum in the middle of your semiconductor. Ganyan ang magiging itsura ng electric field intensity natin. What will the voltage look like? So the voltage now is the negative of this area naman. No? Negative nitong area. So initially, your area is 0. Okay. As you go toward the right, your area increases, but increases first slowly. And then the area, okay, increases quickly. Here, the area increases most quickly. And then the rate at which the area increases slows down kasi ito pababa na. So the area will increase, the increase in area will slow down until at this point, your area will no longer increase. No? So this is what your voltage along your non-uniformly doped n-type semiconductor will look like. The voltage will be 0 at the left side, and it will be negative at the right side. Does that make sense? Negative at the right side? Yes, no? Because remember, your electric field is toward the right, toward the right. That means you have positive charges on the left and negative charges on the right. Therefore, you expect the right side to be negative with respect to the left side. No? So, inulit ko lang itong voltage dito, dito. what do we want to find out next? No? The potential energy. What is potential energy? Negative for electrons. No? For electrons, it's negative E times V. So ito ngayon yung potential energy. And we already said that this acts like an energy barrier. No? In other words, if I have a certain amount of energy here, okay, don't expect it to be able to go beyond, no, beyond that point. No? So for example, if I have this much energy for an electron, don't expect it to be able to move beyond this point. No? Okay. So that is your potential energy. This is your potential energy profile. And remember what we said, ano? That the potential energy for electrons is actually EC. No? That is the minimum energy that you have to impart on a valence electron, no, to be able to, or that a valence electron must have to be able to exist in the conduction band. Kung yun lang yung energy ng valence electron natin, don't expect it to be moving because it only has enough energy to go up to the conduction band. And you can see that in this particular case, E's of C will be changing. E's of C will be changing. Okay. But then E's of V will also be changing because E's of V will just follow E's of C. And your intrinsic energy level, no, will also be following your potential energy profile. So this is now going to be the energy band diagram of this particular non-uniformly doped N-type semiconductor. Ito yung magiging itsura ng energy band diagram niya. This is in thermal equilibrium. If it is in thermal equilibrium, it can only have one value of Fermi level. So this is going to be your Fermi level will be maybe here, no? Somewhere here, Fermi level. Remember that this is N-type. Naalala nyo N-type? Pag N-type, your Fermi level is greater than your intrinsic Fermi level. Your intrinsic Fermi level, E's of I. It when you dope with donor impurities, your Fermi level goes up toward EC. Okay, so I just wanted to show you how when you have a non-uniformly doped semiconductor, you actually have what we call band bending because your bands, no, imbis na being flat, will now bend, no? And now there's some significance to this axis now, no? This is now your x-axis. Dati-dati yung pinapakita nating energy band diagram, wala namang ibig sabihin yung baba, no? But now we show you that your energy band diagram can actually be changing along the x-axis. Your energy band diagram profile can also change when you apply a voltage across your semiconductor. So let's assume that we have a uniformly doped, so hindi na ito non-uniformly doped, no? Uniformly doped N-type semiconductor to ngayon, ano? And let's assume that we apply a voltage. Okay, the same voltage, ano? But this time let's put the reference here. No? It doesn't actually matter where you put the reference, no? You can put the reference on the left side, you can put the reference on the right side, but in this particular case, ilagay na lang natin yung reference dito so that our plot does not end up being negative. So this is now the plot of my voltage along this non-uniformly doped N-type semiconductor. No? So here my voltage is 0. If I try to probe the voltage as I go toward the left, parang potentiometer. No? If I try to probe the voltage, halfway it should be V sub x over 2. At this point, it should be equal to V sub x. So what will the potential energy for electrons look like? It will just look like this. No? So the applied voltage creates an increasing potential energy profile for electrons. And we already said that the energy band diagram follows the potential energy profile. No? So kung ito yung potential energy profile, the shape of EC will take the same shape. The shape of EI, the shape of EV will take the same shape. Okay, take note that this is not thermal equilibrium because you have an applied voltage. So there's an external force applied. The voltage creates an electric field. Um, the electric field causes a force to be experienced by the electrons. No? So if it is not in thermal equilibrium, don't expect to have a single value of Fermi level. As a matter of fact, this is how your Fermi level will look like. It will also follow now the um, potential energy profile for electrons. Okay. Now, what actually happens in this particular case? No? This particular case, you actually have a current flowing in the counterclockwise direction. No? What does that current consist of? That will consist of holes moving from left to right and electrons moving from right to left. No? Holes moving from left to right and electrons moving from right to left. That is your current will be in the counterclockwise direction or moving left to right along the semiconductor. No? So the holes will actually, the electrons will actually, like I said, moving from right to left will actually be falling, and the holes will be floating. Okay, remember what he said that the electrons tend to go toward a lower energy level. Actually, also holes tend to go toward your lower energy level. Okay, if this had been a vacuum, this would be accelerating. No? But because there is scattering, instead of accelerating, this will just be falling at a certain mean velocity, and the holes will be floating at a certain mean velocity. So we already took that up. This is your drift velocity, which is the average velocity that your electrons or your holes will flow in the semiconductor. So this is now what will sustain the current in this particular situation. Okay, but what I wanted to point out here was that an applied voltage also causes band bending. So you can have band bending because of the non-uniform distribution of dopants, or you can also have band bending because you applied a voltage. Okay, we discussed that so that we can apply now these principles to a PN junction. That is what we actually want to do. So let's take up the PN junction. So from 1 to 3, you know that a PN junction is formed, no? Or a PN junction is a junction that is formed between a P-type and N-type semiconductor. No? So in this particular case, your P on the left and N on the right, no? So this is your junction. Okay? Note that you cannot physically paste a P-type and an N-type together. The crystal lattice structure of the semiconductor must be maintained as you're going from P to N. And because of the level of doping, if you were a very small person and you enter the semiconductor, you wouldn't even know when you left the P and when you entered the N, because of the very low level of doping. Remember what we said? Um, you have maybe one dopant for every 10 to the 5 or 10 to the 6 10 to the 6 atoms. Okay, so you wouldn't know when you left the P and when you got into the N. So we know this to be the characteristic of a PN junction. It has rectifying properties. Current easily flows from P to N. It is difficult for current to flow from the N to the P. And this is the circuit element that is used to represent the PN junction. We call it a diode. And this is the symbol. The left side we call the anode, the right side we call the cathode. So this is how you might be able to create a PN junction. One of the ways. It is not the only way. You know? Starting point can be an N-type. Okay. Starting point can be an N-type. You put this in a diffusion furnace, and one end of the N-type you expose to acceptor impurities in gaseous form, no, in very, very high temperature. No? The temperature should be high enough so that this is semi-molten. No? It is still a solid, but it's already liquefying. No? But you don't actually want it to melt, because if it melts, it will lose its crystal properties. So it is semi-molten. But because of that, it's easy now for your impurities to dislodge certain certain nuclei from the crystal lattice and to replace themselves with the nuclei that they dislodge. No? So papasok dito sa end na to ang acceptor impurities, and it will diffuse into your semiconductor. No? Okay. So this might be how your impurity concentration will look like after after a while. Okay. This is your original concentration, N sub D. That is your original concentration. Okay. And then this is the acceptor concentration that is introduced by this diffusion. Okay. Expect this expect these impurity atoms to diffuse. Okay. At some point, the number of diffused acceptor impurities will equal the number of donor impurities that were originally in the semiconductor. No? Okay. But then as you go more toward the right, syempre, this is diffusion, ano? Your diffusion really slows down so that eventually your acceptor impurity concentration becomes practically equal to 0. So this is the initial acceptor concentration, which is Na plus Nd here, no? Numerically, no? Numerically equal to Na plus Nd. Here, Na is equal to Nd. This is going to be your net donor concentration. Net donor concentration. No? So initially here, your net donor concentration will be negative Na. What is your net donor concentration? It is Nd minus minus the acceptor concentration. The acceptor concentration here is Na plus Nd. No? Hindi Na, no? The acceptor concentration here is Na plus Nd. So Nd minus Na plus Nd, you get minus Na. Okay. And then eventually the net donor concentration becomes 0. And then eventually, as you go to the right, no, your net donor concentration will become equal to Nd. No? So remember, itong Na na to is your net acceptor concentration. It is not your absolute acceptor concentration. No? That's very important. It is your net acceptor concentration, not your absolute acceptor concentration. Okay? Okay. Ito ideally, this is what your net donor concentration should look like, no? It should be NA to the left of the junction and ND to the right of the junction. No? So this is the ideal. This is the actual. But we're going to, okay, so this is now your PN junction. No? So this is now P-type and this is now N-type. No? But we're going to analyze this assuming that you have a step junction. Naturally, it can be shown in the references that when you do that, you don't actually lose much accuracy when we assume a step junction. Okay, so what happens? At the instant the junction is created, these are what your energy band diagrams look like at the P side and at the N side. At the P side, okay, this is your forbidden band. And because this is a P-type, your Fermi level at the P side will be between EI and EV. At the N side, again, this is your forbidden band, and your Fermi level at the N side will be between EC and EI. So this is at the instance of creation of your junction. Now, what will happen? What will happen? Okay, you have predominantly holes here. You have predominantly electrons there. So you have a non-uniform distribution of carriers. So actually, you can think of this as a non-uniformly doped semiconductor. No? Kagaya nung non-uniformly doped semiconductor na diniscuss natin kanina. No? Except that in this particular case, your non-uniformly doped semiconductor is uniformly doped on the left side and uniformly doped on the right side, but the doping is different. On the left, it's holes, and on the right, it's electrons, or left is acceptors, and on the right is donors. No? So at the instant that this is created, because it is non-uniformly doped, there will be diffusion. Ano ang magdi-diffuse? Yung holes natin, magdi-diffuse mula kaliwa papuntang kanan. Yung electrons naman natin, magdi-diffuse mula kanan papuntang kaliwa. So this is going to be diffusion. Okay, if there is diffusion, yung inalisan ng mga holes become negatively charged. No? Yung inalisan naman ng mga electrons nagiging positively charged. So you see a charge build up. No? Here, positive charge build up. Here, a negative charge build up. And whenever you have a charge distribution, as in the previous example of a non-uniformly doped semiconductor, you will have an electric field. No? There will be an electric field from plus to minus. Okay, ito yung electric field. What happens when you have an electric field? When you have charges in the presence of an electric field, those charges will experience a force. There will be drift. Ano ang magdi-drift? Ang electrons will drift opposite the direction of the electric field. Holes will drift, no, in the same direction as your electric field. So that is now your drift. Eventually, the holes and the diffusion and the drift will cancel out each other. Eventually, it will cancel out each other so that your net current is going to be equal to 0, which has to be the case because this is open circuited. There cannot be a current flowing in this particular material. No, so at some point, the diffusion and the drift will cancel each other out. No? But then there would have to be an internal electric field in this vicinity that will stay there. Because if this electric field disappears, okay, mag-uumpisa uli yung diffusion, magkakaroon uli ng difference in charge density profile, magkakaroon uli ng electric field, magkakaroon uli ng drift. No? So there has to be at steady state, there has to be an electric field that will stay here. Okay, that electric field actually stops building up when diffusion and drift become equal. there is a region in the vicinity of the junction that becomes depleted of mobile charge carriers. In other words, lahat ng electrons dito sa region na to nawala. Pumunta dito sa P side. Tsaka lahat ng holes dito nawala, pumunta dito sa N side. Okay? Why did I draw here uh, the region larger on the N side than on the P side? No? It's because your P side and your N side are not uniformly doped. No, it's not. They're not uniformly doped. No, in other words, the implication here is I need holes from a smaller area to cover electrons here in a larger area. No. That means that n my n my n in this particular case is actually more likely doped with my p, no? Because my holes here in a small area will cover the electrons in a larger area. Anyway, what do we call this? We call this the depletion region. And in the depletion region, we approximate the electron concentration to be equal to the hole concentration to be equal to 0. And there will be a large electric field, a relatively large electric field in this direction, the direction being from your N side to your P side. Now, outside of the depletion region, there will be, you call this the quasi-neutral region here and here. There will be no electric field there. The electric field in that region is going to be equal to 0. So let's apply the principles of electrostatics, which we earlier discussed. This is going to be your approximate charge density profile. We are assuming here ideal ionization. So again, we assume a step junction. We assume ideal ionization. So this is going to be negatively charged kasi inalisan ng holes dito, and this is going to be positively charged kasi umalis yung mga electrons dito. Okay, what will our electric field intensity look like? Remember, it is proportional to the area under rho. That area, if this is flat, will be linearly increasing. No? As we go from here to here, your area will be linearly increasing. And then at this point, okay, your area will start, sorry, your area will be linearly decreasing. At this point, your area will start increasing. No? Negative area dito, you're adding a positive area here. So yung negative, unti-unting nagiging mas positive hanggang yung area natin, total area is equal to 0, no? So this negative area must be equal to this positive area. Okay? So this is how your electric field intensity will look like. What will the potential look like? What will your electric potential look like? No? That's equal to the negative of itong area naman. No? So this is going to be the electrostatic potential across the depletion region. We call this your built-in potential or VBI, built-in potential. No? And what will your potential energy profile for electrons look like? That is the negative of your voltage multiplied by E. So ito yung magiging itsura niya, no? Ito yung magiging itsura niya. Okay? So that is the electrostatic analysis of your PN junction, no? So your energy band diagram will actually have this shape as you go from the left to the right. Okay? So this is your energy band diagram at the instant of junction creation. And this is now how the energy band diagram will look like. So itong shape na to is the same as the shape. It's the same as the shape. That's your energy band diagram. And note, This is in thermal equilibrium, and therefore you can only have one Fermi energy level, and that is going to be this Fermi energy level. Okay? So what happened? Actually, itong EFN at saka EFP nag-align. It aligned. No? At the instance of creation, they are unaligned. Okay? And then what happened? Okay? Because of electrostatics, bababa yung potential energy sa kanan, no? And then magiging aligned na yung dalawang E's of F nila. The Fermi levels align. Okay, what is going to be the total displacement, no, of EC from the left side to the right side? That is going to be Q VBI. No? That is kasi energy, no? E sub C is energy. So the difference in energy from the left side to the right side will be equal to Q VBI. Ano nga ba yung VBI? Ito, no? Ito yung teka, asan ba yun? Yeah, no? Ito, sorry. Ito yung VBI. No? The built-in potential. The potential that is caused, that results because of the electric field that will build up because of the charge distribution profile that will happen because of diffusion. So that is this, no? Can we compute for that? Yes, we can. No? How can we compute for that? We have these formulas that we studied in the last module, right? P, the whole density here, is approximately equal to Na. Ano yung Na? Remember, Na, I said, is the net acceptor concentration. No? So I just want you to take note of that. This is the net acceptor concentration. No? So P is going to be approximately equal to Na. Okay, we're assuming that there's total ionization. And then you have this formula. Remember this formula? Ni is of I minus is of F over KT. Ito naman, well, this should be net donor concentration, but in the N side, we assume that Na is equal to 0. So this is actually the actual donor concentration. So N is equal to Ni e to the EF minus EI over KT. No? So this is for the P side. This is for the N side. No? If you multiply these two equations together, you get Na Nd divided by Ni squared. Okay. So, well, una, this is going to be NAND is equal to Ni squared e to the EI minus EF over KT multiplied by e to the EF minus EI over KT. If you simplify this, ito yung lalabas, no? NAND over Ni squared. Yung EF magka-cancel out kasi ito negative, ito positive, right? When you multiply these two together, then you can just add their exponents. So this will cancel out with this. Ito na lang yung matitira. And therefore, we can compute for EIP minus EIN. No? EIP minus EIN, itong level na to minus itong level na to will actually give us Q times VBI. And you end up with this particular equation. KTLN NAND over Ni squared. If we divide KT by Q or KT by E, that becomes V of T. You know, remember the definition of thermal voltage, KT over Q. So the actual built-in potential will only depend on your concentrations and your intrinsic concentration. Now note that this cannot actually be measured directly. No, there is no way you can probe a semiconductor to determine what VBI is, because the minute you probe a semiconductor, nagkakaroon ka rin ng some potential between your probe and the semiconductor. No, so anytime you do that, no, if you have a way of probing the voltage without actually making contact with the voltage, then you can measure VBI. No, but if you're probing it, you will not be able to measure VBI. Okay, so this is an important equation, something that you have to be familiar with. No? So let's take an example. Determine the built-in potential of a silicon p-n junction at room temperature if the p side is doped at Na equal to 1 times 10 to the 17 centimeters to the minus 3, and the n side is doped at Nd equal to 2 times 10 to the 15 centimeters to the minus 3. So assumption here is this is already your these are already your net concentrations. No, in other words, this assumes that Nd is equal to 0 on the p side, and this assumes that Na is equal to 0 on the n side. So actually quite trivial. So VBI is b sub t ln NA over Ni squared, and if you do the computation, it will be 0.715. Maybe that number 0.7 is something familiar to you, and the answer is yes. No, the voltage drop across a PN junction is actually affected by itong built-in potential. What will happen if we apply a voltage across your PN junction? So we now say that your PN junction is biased. So let's assume that we apply a voltage V sub A with the P positive with respect to N. By the way, no, in real life, don't do this. No. Um, in real life, you're not supposed to do this because if V sub A is very much greater than, for example, if this is silicon, if V sub A is not even very much greater, no, is greater than 0.7, chances are you're going to destroy this diode. No, in real life, whenever you put a voltage source in series with a diode, you would have a current limiting resistor. But we skip that for now. No, we just assume that we have control over the value of V sub A so that the diode will not, so that the PN junction will not burn out. Okay, so we already know this. When V sub A is greater than 0, it is forward biased. If it is less than 0, it is reverse biased. And if we assume no voltage drop across the quasi-nuclear areas, no voltage drop here, no voltage drop here, the whole of VA will be felt across the depletion region. No? So this will be imposed only across the depletion region. No? So when forward biased, so this is a caveat, no? When forward biased, VA should be less than VBI for the PN junction to operate as desired. So this is related to what I earlier said. If you make VA much greater than VBI, chances are you're going to destroy this diode. So ito yung forward bias, ano? Ito yung equilibrium, open circuit junction at equilibrium. What happens when you forward bias it? You're making the P more positive with respect to the N. In other words, you're making this internal voltage, no, this internal voltage smaller, no. This becomes smaller by V sub A, no. This becomes smaller by V sub A. That is when you forward bias it. Okay. Notice that now your Fermi levels will no longer be aligned. And that is understandable because your semiconductor is no longer in thermal equilibrium. One of the things that will happen is the width of your depletion region will decrease. So this will become smaller, and then the width of your depletion region will decrease. What happens when you reverse bias your junction? Again, this is your open circuited junction with your built-in potential, VBI. Reverse bias, so you're applying a positive at the cathode with respect to the anode. So this will increase by V's of A. And the width of your depletion region will increase. The width of your depletion region will increase. Okay, I want to show you a qualitative analysis of the currents that will flow. So this is your open circuited PN junction. Your Fermi levels align. Okay, what are these? These are your electrons, and these are your holes. Okay. Okay, there are more. Let's take a look at electrons. No, electrons lang muna. There are more electrons here than here. So the tendency is for electrons to diffuse from right to left. No, electrons can diffuse from right to left. But remember that this is a potential energy barrier. No, if your electrons do not have enough energy, they will not be able to they will not be able to traverse the path from left to right, no? So for example, itong mga electrons na to, it will try to diffuse to the left, it will just hit the barrier. Hindi siya makakalusot dito. Ito, it will also just hit the barrier, no? Hindi rin siya makakalusot. Ito lang yung makakalusot, no? So itong electron this electron will be able to jump to the other side, no? So makakalusot yan dyan. Okay, what about this particular electron? Right? What this electron sees now is an energy barrier that is decreasing. In other words, no, it will try to move. Remember what we said, the electrons will try to move to a state of lower energy. No? When it sees this decreasing energy barrier, it will have a tendency to accelerate toward the right. No? Because toward the right, its kinetic energy will be increasing. But of course, we said it will not really accelerate, or it will not really have a chance to accelerate that much because of scattering. No? But the case is that this electron will be able also to move this way. No? Now note that you have one, in this particular illustration, you have one electron that can move to the right. You have one electron that can move to the left. They cancel each other out. In the same situation here. Remember, holes tend to float, electrons tend to sink. So these holes will tend to float, no? But then, this will not be able to float up kasi ito tatama din dito, no? Hindi siya makakalusot dyan. Ito lang yung makakalusot. Ito naman will be able to drift. No? So remember, this is diffusion. And then this is drift. No? Ito, this is drift. This is diffusion. That's what will happen. No? So, here, the number of electrons that can diffuse from right to left equals the number of electrons that can drift from left to right. No? Similar situation with holes. So your net current is 0, which is the case for an open-circuited PN junction. What will happen if we forward bias it now? No? Remember, we forward biased it so that lumiit lumiit yung difference between EC on the left and EC on the right. Ngayon, lahat nito makaka-diffuse. No? Itong isa, ganun pa rin, makaka-drift. Right? Ito, hindi makaka-diffuse. Tatama sa energy barrier. Ganun din to. Ito hindi makaka-diffuse. This can diffuse. And then this can drift. Okay. More electrons can diffuse from right to left than can drift from left to right. Same thing with holes. No? So there will be a net current that will exist from left to right, primarily due to diffusion. Why is the net current from left to right? No? Holes will diffuse from left to right. That's the direction of current. Electrons diffuse from right to left. So the direction of current is left to right. Okay. So you can see the difference. No? Here, zero net current. Here, net current. What is the current composed of? No? Charges that are diffusing. So in a forward biased PN junction, current is actually due to diffusion. It is not due to drift. Again, no? In a forward biased PN junction, current is due to diffusion and not due to drift. What happens sa reverse biased? So this is the equilibrium. So we already explained this, ano? No net current. Pag reverse bias, ito dati nakaka-diffuse. Pero ngayon, lahat ito babangga dito sa energy barrier. Lahat nito babangga dito sa energy barrier. Ito makaka-drift pa rin. No? So you still have drift here. This will also be able to drift here. No? So ano sinasabi natin dito? No? Electrons cannot diffuse but can drift. Similar situation with holes. So there will be a net current that will exist from right to left. No? Because you have electrons drifting toward the right. Yeah. Electrons drifting toward the right, you have holes drifting toward the left. So there is a net current from right to left. No? Same direction as holes, opposite the direction of electrons. So meron palang current sa reverse biased. Sa reverse biased diode. No? Di ba sabi natin sa 1, 2, 3, when your diode is reverse biased, your current is equal to 0. Well, hindi pala totoo yun. No? There will be a current that will flow in a reverse bias diode. But what is that current due to? Bakit ba may electron dito sa P side in the first place? No? Because those are thermally generated electrons. In other words, they're the intrinsic electrons. Ito rin, ano? Thermally generated holes. And we know that that is very, very small. No? So the current that will flow in a reverse bias PN junction is actually very, very small. No? Practically equal to 0. As a matter of fact, later on, you're going to find out that this current is maybe in the vicinity of 10 to the minus 9 or 10 to the minus 12 amperes. No? So for practical intents and purposes, that is considered to be equal to 0. Okay, so that is a qualitative analysis of current flow. So again, to review, when forward biased, you have current flow from anode to cathode, and that is due to diffusion. When reverse bias, you have current flow, this time from cathode to anode due to drift. But that current flow, when reverse biased, is very, very small. So here are the key takeaways. In a non-uniformly doped semiconductor at thermal equilibrium, you have band bending. That is because there is an electrostatic potential that is induced across your semiconductor by diffusion. You can also have band bending induced by a voltage across a semiconductor. So band bending causes a built-in potential to exist across the depletion region of a PN junction. The built-in potential decreases kapag forward biased and increases kapag reverse bias. So in a forward biased PN junction, diffusion exceeds drift and current flows from anode to cathode. In a reverse biased PN junction, drift exceeds diffusion and current will flow from cathode to anode. But because these are composed of minority carriers, it is very small. And practically negligible. Okay, so that's the end of this lecture. Okay, I will I will see if I can post the next lecture. Okay, but please go through this particular lecture again if you feel that some points were not very clear. Okay, that's it. Thank you for tuning in.